All right, for this paper, stellar metamorphosis transformation curves on a Wolinsky-Taylor diagram. Another pretty picture here. A lot of information can be gathered from this. I wanted to go over transformation curves because they're essential to understand that the star is very similar when it's young, but as it evolves, it goes down different paths and can change based off of its orbital parameters, based off of how much material it's managed to collect, based off of how much matter has been lost, how much differentiation has occurred. And we can determine that and go in the past and into the future, ideally with a transformation curve. Now, transformation curves are going to be all different, or different for all stars. And if you notice on this diagram, I have a lot of words on here. But firstly, I'll link this to the bottom so you guys can read along with me. Starting with number 1. Each star has its own unique transformation curve. Think of the transformation curves as being the DNA of the star. DNA meaning, sure, you could have two people look very similar, but if you take their DNA, you'll find out that one star is not the same as another, even though a lot of it matches. You know, they have brown eyes, brown hair like me, or they're male, or they're Caucasian. A lot of those match, but you take a random white, brown eye male off the street, I guarantee you're gonna look at him and be like, wait a second, that's not the same. Same thing with stars. When you look at a star that has a similar mass, similar diameter, similar elemental composition, there might be some other things off about it that differentiates it from the other star. Number 2, there are no step transformation curves. They are continuous. The differences between transformation curves are not discrete and static, but continuous and dynamic. A discrete meaning stepped, like think of like a stairwell where you go down, over, down, over, down, over. It doesn't work like that with stars. It isn't, oh, Jupiter, and all of a sudden it loses all its mass at the same time, and then it ages. Or like a third of its mass, and then it ages, and then it loses a tenth of its mass, all at the same time within like a few seconds, and then it ages. It doesn't work stepped. It works continuous. The Jupiter is continuously losing mass as it evolves very, very slowly. And that's a very important concept to learn because the transformation curves are dynamic. And also dynamic. So they're continuous, they're smooth, and they're dynamic, meaning it could be a smooth one, and then it could have an impact event when it's very, very old and shatter apart and make a whole bunch of baby transformation curves. I have another diagram I want Baz to draw up for me. Baz, if you want to do it, it's cool. You'll see what I'm talking about when you see it. But it's very important. That's going to be another thing. Get off tangent here. Number 4, you cannot have a star on a transformation curve and move that star to the next higher transformation curve. And that being said, that rule basically applies to the fact that you can't, say you're on the yellow and black curve, you can't move up to the green and black curve. If you're down here, you're going to continuously move down here. If you're up here, you're going to continuously move over here. But you can't go up because that is outlined in a simple law the law of conservation of mass. If you have a net loss of mass of an object as it's evolving, it's going to be less massive. So if you are going to move up a transformation curve, which is highly unlikely, you'll have to be gaining a hell of a lot more mass than you're losing. And that would be absolutely phenomenal. But I guarantee you it's never going to be observed. What's actually observed, the stars, they move slowly down a transformation curve and they lose mass as they evolve. Number 5, the similarities of transformation curves is closer the younger the star, and the similarities can decrease statistically as they grow older and evolve. So what that means is if you start way up here when the star is very young, the possibilities for the star are a lot higher. They're all similar when the star is very, very young, big, hot, and bright. and the similarities they're really really close together. No matter how, if they're all about the same age, the same level of differentiation, the same mass. But as they evolve, the similarities start popping up because of material that comes into the star, the material that exits the star, and then they evolve by great amounts. By the time they hit this little black area, they're about 350 million years old. But you know, from shining to not shining anymore, and shining brightly anymore. And as they move down here, their range of differentiation, their range of different elements that they're mostly composed of, expands significantly. This is why we're going to have many different stars, all different. We're going to have stars that are way more massive than others, but be the same age, and you're going to have stars the same mass to each other, but actually very different in age. This is where the real differences come into play. And that goes into number 6. And number 6, if you'll read number 6, I have 2 stars, one star at 3.5 billion years old, and another star at 17 billion years old. Those little black dots right there. So on the y-axis, I have, total mass. And those 2 little black dots there, the reason why I put those there is 3.5. No, that's not 5. It's not 5. It's 3.5. 3.5 billion with that black dot. The 5 goes to that little that black line right there. So 3.5 billion and 17 billion. You can have 2 stars on 2 different transformation curves. Now they're the same mass, but due to their position on the graph, we can see that they both, one has evolved a lot faster than the other to get to that same mass. So they could be the same mass, but what will happen is, since they're on different transformation curves, they're not going to have the same level of differentiation. They're not going to have the same amount of hydrogen in their atmospheres. They're not going to have the same amount of DH ratios. All those other variables are going to be different. So when scientists, they say, well, they found the orbit of a star around an evolved star around a young one, they're going to say, well, this one is this massive. Okay. And then they're going to find a second evolving star around that host, and they're going to say, oh, this one is the same mass. So they find 2 objects that are the same mass. One orbits close and one orbits a little bit far from their host star. And then what astronomers do is they say, well, they must be the same age, because, well, how do I word this? A lot of their physical characteristics must be the same, and they probably are the same age because they orbit around the same host star at the same time. But that's completely false, because due to the transformation curves, you can have a star at 3.5 billion and one at 17 billion years old. It's just this one evolved a lot quicker than the other one. So the other one is a lot older, meaning you can't really tell. You have to actually physically examine the star, and you can't determine all its properties based on its mass. I'm gonna beat that one into the ground. Number 7, the cross symbols are used to show that 2 stars can be on a very similar transformation curve as another, but have different masses, ages, and a host of other different properties. This is very important too. If you have, okay, let's take the top ones right there on the green curve, green and black curve. You have those 2 right there. One is clearly vastly older than the other. One is a lot less massive than the other. But that's the crux of this theory. You can't look at 2 individual stars and say they're different and that they have formed from different processes, when clearly they are on the same railroad track here. They're not different. One will become like the other, for the most part. Now, that's the ideal, given all the conditions are going to be similar as the other. It might be a little off, and might scoot a little bit further down than the other one currently is. But that is the crux of the issue here, is that you can't take a star and say, this is how it's always been, this is how it will always remain, because they evolve, the planets evolve. And their evolutionary tracks, the transformation curves, show that quite clearly. There's that. Quickly, number 8, the term hot Jupiter can be a star that is getting ripped apart by our hotter host. Hot Jupiter would be a good example of a star that is moving on a faster transformation curve. So hot Jupiter could be a star that moves way down here on this red curve and just gets blasted by a host, so it evolves really fastly and becomes nothing significant because its atmosphere is ripped away. And an ice giant, I guess an ice giant, could be a star that's way the hell up here and evolves very slowly because it stays away from a hotter host and it's always in outer space, so it can build up the core to very, very large amounts as it evolves, making a very, very large Earth would be way up here somewhere. The transformation curves are ideal. I use the word transformation based off of Anthony J. Abruzzo's paper. I linked that right here. Of course, he had a similar idea. I don't really know how much further he's designed it. I haven't been able to find any new work that he's produced, so I'm basically just doing this. Number 11, as is noted, stars cannot have their ages set to their host stars because they are highly evolved stars themselves, as noted in the general theory. This is very important. Quickly. The host star, a red dwarf, okay, and then say the TRAPPIST stars all orbit around it. The 7 older, highly evolved stars are orbiting around it. What the establishment does is say, we know how old the red dwarf is, and that means all the 7 TRAPPIST stars around it are all the same age as this one. But if you look at this graph, that's literally impossible. A red dwarf would sit right up here. And all 7 of those highly evolved stars sit somewhere over here, which all could be very different ages, and also are by default very different ages. They sit between 5 and 25 billion years old, or maybe even a little bit younger over here. But all right, I think that sums it up for this talk. Guys, take it easy.